had come to my own conclusion earlier on. I had thought, well, because I was a ski instructor and I climbed as well a lot. I love climbing. And I was in nature all the time. I thought, well, if I want to know the structure of the vacuum, if I want to know the structure of space-time at the vacuum level, and if nature is being directed by that structure, I should be able to observe nature and see it. I should be able to deduct it from a good observation of nature. So I was always looking at snow crystals, and when I was climbing at the crystals on the rock, and I was always looking at things and the way branches divides in a tree and all this. And I had come to conclusions that the universal forces, the vacuum division, seemed to always generate a very fundamental, specific geometry, and that geometry was the geometry of a sphere. It makes spheres, little spheres, and bigger spheres, and then assembles them together and gets all sorts of things. But I was thinking, wait a minute, though. The sphere would be the part that's on the outside. The sphere would be the event horizon. The sphere would be the boundary from which things radiate. What I want to know is what's inside that. I want to know what's the geometry that holds the sphere together. How does the sphere pop out in the vacuum? And it wasn't obvious, but I started to study geometry and I realized that the sphere is the most unstable geometry. It's got the most surface and it doesn't have structure, so it's the most unstable geometry. So how would it hold together? And I thought, well, it has to have the most stable structure in the middle. And not only would have to be the most stable structure in the middle, whatever the structure was that was holding the sphere, that was dividing the vacuum, that structure had to be in perfect equilibrium. Because it had to be able to be observed as the vacuum. That is, if it had infinite amount of density, at the end of the day, when all the density, all the vectors of the geometry would collide at that level, the geometry that would result would have to be in perfect equilibrium so that we would think that it's empty space. That we would think that it's a vacuum. So all that logic had come through, and so I started to study what would be the smallest, the most stable, the most equilibrium geometry I could find. And what I had found is that the exact opposite of the sphere, which is the largest and most unstable, was the tetrahedron. And if we look at a tetrahedron, it's made out of, it's the smallest volume possible, okay, with equal edges and equal faces. And it's made out of 3 faces on top and 1 on the bottom. So 4 faces generates, it's like a pyramid with a triangle base. And this is actually the most stable, fundamental, and the most fundamental geometric structure we can find in nature or in geometry. So I thought, well, okay, it probably has something to do with the tetrahedron inside a sphere. And I had come to those conclusions. So I didn't know why all these ancient people were building pyramids. But I thought maybe when I go home, I'll study it and research a little ancient text and stuff like that. So I go home. I'm living in Whistler, right? And I, went to my local library, which wasn't much. I mean, this is a ski resort. And I'm looking around, and this book pops out at me, and it's called Mystery of the Mexican Pyramids by Peter Tompkins. And I thought that was an appropriate title because I really felt there was some kind of mystery going on there. So I pulled out the book and I opened it randomly, if there is such a thing. And it opened on page 280, I believe. And it had this graphic on it. A tetrahedron inside a sphere. This was the first time I was starting to study ancient texts, and that's the first thing I found. Actually, the solution that I had come up with my own logic and my own geometry and my own math on my own. So I started to read, and I got the original papers, and I realized that this graphic came from the result of a 20-year investigation of the plaza and the pyramidal structures that are found north of Mexico City. And it has the moon pyramid, the sun pyramid, and the person that did the survey there, did it for the American Society, is Hugh Hollison Jr., I believe. And he came to very amazing conclusions. First of all, when he started to map the whole city at Teotihuacan, he found that the sun pyramid and the moon pyramid and all the other buildings seems to be in appropriate relationship to each other, so to reproduce a map of the solar system, including Pluto and Neptune, which were planets that we didn't discover in modern age until the early 1900s. So that was very amazing to him that these people would have that knowledge of that. It was very compelling. And he started to, he spent 20 years there surveying the whole thing, and he started to find that there was very specific ratio relationship between the buildings and how they were placed and mapped and all this around the world and around the whole city. And he thought, there's some kind of fundamental code that's being used here to build all this, and maybe there's some kind of fundamental message. And after 20 years of research, he delivered his papers to the American Society, and in it, he mentions that according to his mathematics and the way he mapped this, it seems that everything seemed to be pointing out that we should be looking, or that the mathematics that they use had to do with a tetrahedron inside a sphere. This really stunned me. It was amazing. I mean, I thought I was going to copyright that stuff, and somebody had come up with it a few thousand years before me. It was right there in this book, and so that really got me going in studying ancient texts. But more importantly, at the time, there was a comment that was made in that book that the fundamental equation that Hugh Hollison Jr. used to map this out match a very specific mathematics of Buckminster-Fuller, which related to an isotropic vector metric. And the isotropic vector metric is made out of 20 tetrahedrons. There's 10 on the bottom, 6 on the second level, 3 on top, and 1 on top. It's actually a 4-frequency isotropic vector metric. This fundamental geometry was part of Bucky's concept that the universe had a mathematical geometric blueprint to it, so something very similar to my thoughts, and that blueprint related to this very specific metric. So I got very excited and I started to study it in detail. I looked at it in different angles, and I started to think, well, okay, so if I'm not dealing with just one tetrahedron, then there must be the interaction of the tetrahedrons may have different geometries involved in it. And since I was really investigating the structure of the vacuum, I was very interested in the negative space between the tetrahedrons. So I eliminated the tetrahedrons from the space and extrapolated what was in the middle of it, in between the tetrahedrons. And what I found is that what's in between the tetrahedrons is octahedrons, right? Now, an octahedron is a double bonded pyramid, okay? Emphasis on the word pyramid. This is the cavity between the tetrahedrons of the isotropic vector metric. Can everybody see them there? They're tilted like this, okay? And you could think of, for instance, if we look at this top one of the points of the pyramid is up here, the other point is back here somewhere, and it's on an angle somewhat like this, right? For you guys to look at. Everybody sees that? Oh, not quite, like this, right? Okay, so I was excited. Oh, here's the pyramids. It kind of linked with the ancient concepts. Okay, well, that's interesting. And then as I kind of traced all the vectors of the pyramid and in my drawings and in my head, I didn't have a computer at the time. I realized there was some strange negative cavities inside the isotropic vector metric. So here's our isotropic vector metric, and here's the cavities that I noticed that were inside it. Now, if there's 20, so let's put it this way, and if we look in between, there's our octahedrons, okay? But in red here, we've demarked that actually there is another set of tetrahedrons in the middle that are pointing inward, that are pointing down, right? And that are rotated from the initial metric. When I found those, I was surprised because this is thought to be an isotropic vector metric. I thought that must be the same everywhere. There shouldn't be any asymmetry. And certainly, I was looking for the geometry of the vacuum. So I was certainly looking for something that was in equilibrium and couldn't have asymmetry in it. So I was surprised. I didn't know what to do with these cavities in the middle. They didn't belong to the octahedrons, and they didn't belong to the tetrahedrons that were pointing up. So I thought, well, there's one thing for sure, is that if the universe is polarized, it cannot be that the geometry of space would have only one polarity of the equation. It would have to have both sides of the equation, and I had to add the reverse metric to it to get the polarity, the male, the female, the plus, the minus, the white, the black, and so on. So I added another metric below it, but when I did so, if I put one metric base to base to the other, if I put another one base to base to this one, then I have another problem. And that is, I don't get a sphere. I get an egg-shaped structure. And I was looking for the sphere. So this was like a chicken and an egg problem, and I was very confused. I was spending a lot of time on this. I'm walking you through things that took years because I was working to survive at the same time. Eventually, I quit my job, sold all my ski equipment so I could move into a van and sponsor my own research with very little cost. And so I was in my van thinking about all this. I didn't have a computer. So I've got these matrices in my head spinning, and I'm doing all this stuff with them. And I don't want to distort the geometry of the metrics. I'm not wanting to push them into each other. So I'm resisting that idea, and I'm trying to figure out how they would work. And then eventually, I came to it. I did push one into the other, which took me a while because I had to render all these vectors in my head. And I realized that when they would be in perfect relationship to each other, then I would get a perfect sphere. However, what got me extremely excited is that when when I pushed one into the other and rotated so that it would be in perfect polarization to each other, the central red space that I didn't know were for what were exactly in the right position to accept the reverse metric without having me distort the geometry or remove tetrahedrons or anything like that. So that the polarized metric would actually be incomplete without its better half. And that when the second metric was inserted into it, it would take exactly the spot to create perfect symmetry at the center. And I was really excited because I was looking for perfect symmetry equilibrium. So I started to render in my head what is the geometry of these tetrahedrons coming in the middle. And that's when I realized that the result of the two metric intersecting with each other to create the perfect sphere generated in the middle what is called a cuboctahedron, which is 8 tetrahedron coming together, which was called by Buckminster Fuller the vector equilibrium, the only geometry in which all vectors are in equal proportion to generate perfect equilibrium. I had found the geometry of perfect equilibrium from the polarity of the two isotropic vector metrics coming together. Why is this geometry, for instance, the only geometry that's in perfect equilibrium? Well, I studied a little bit and I realized that actually, if you have vectors of forces and you want to create equilibrium, then you would have, obviously, now, this vector that just popped out could express a force. And we'd say that that force has this specific unit, which relates to the length of the vector. So bigger the vector, stronger the force, smaller the vector, smaller the force. If you wanted equilibrium, you'd send another vector in the exact opposite direction, at the exact same length, and you'd get equilibrium. However, this would be a very precarious equilibrium. Nature could not use that equilibrium because any distortion would make the vector collapse. Any forces in any other direction would break the equilibrium. So it was very unlikely that the universe used that type of equilibrium. Well, what would it do? Because this is unstable. What would it do? Well, if you were trying to get an equilibrium yourself, you would probably say, well, I'll just keep adding vectors. Well, if you add vectors at 90-degree angle from the initial vectors, you're still not going to get equilibrium because now what's going on is that the edge vectors are longer than the vectors to the center, so they're stronger, it implodes, it doesn't work. No equilibrium. So what would you do? You probably continue to add vectors, and you would probably put them at 45 degrees from the initial one. And now you have another problem. That is, the edge vectors are shorter than the vectors to the center. Now the geometry explodes, is still no equilibrium. So what would happen is that you would have to make sure that the geometry's edge vector and vectors to the center are the same length. And the only geometry in which this happens is like the snow crystals, the hexagon, where the edge vectors are the exact same length as the vectors to the center. And if we made a 3D hexagon together, we would get a vector equilibrium, which is made out of 12 vectors radiating from the center and 12 edge-bounded vectors that maintains the structure in perfect equilibrium, or 8 tetrahedrons coming together, all right, to create, a vector equilibrium. So 8 of these coming together to create a vector equilibrium. And so that was really telling. That was really exciting for me. I knew this had to do with what I would have to deal with even if you think in advanced physics, for the physicists here, that, you know, of the structure of space, you could think that the vacuum state is going to infinity. At one point, it would have to reduce to the minimum amount of vector for stability. And that would be 12 vectors. So that's the fundamental basic geometry of equilibrium. But it actually didn't fully work. That is, I still had points on the edge of my metric here. Right? I still had vertices on the edge of my metric that had holes in it. Right? So there was a symmetry. This middle structure with the two isotropic vector metric was completely filled, but the edge was not. So I had still asymmetry. I still didn't have equilibrium. So I started scratching my head some more, and I thought about it, and I thought about it, and I thought, okay, well, my only solution is to continue to add tetrahedrons until I get equilibrium at all levels. So I continued to add tetrahedrons. I covered the spaces that were open on the edge of the metric. So I had to add 3 tetrahedrons to every edge, which was 8. So that generated 24 more tetrahedrons. So remember, there's 20 tetrahedron in one isotropic vector metric. 2 makes it 40, plus 24, added up to 64 tetrahedron grid. And that, when it came to me. At 64, it all came together. Why is that? Because when I put those added 24 tetrahedron in my head as I was visualizing all this in my van, I realized what I had done. I realized that I had generated a vector equilibrium in the middle, but now I had generated a larger fractal vector equilibrium on the edge. And so now I had a metric that was growing from one vector equilibrium to the other, to the other, to the other. And interestingly, they grew in perfect scale of exactly half the radius, so in harmonic scales or in octaves, if you want. And it was a 3-dimensional fractal. This is actually one of the only true 3-dimensional fractal I believe exists. And it grew radially, which is what I needed for the radiation part. And then I realized something even more significant, is that the fractal growth could be generated from 8 star tetrahedron. So 1 star tetrahedron is 8 tetrahedrons coming together to make an octahedron in the middle. Everybody sees that? 8 star tetrahedron, 8 stars like that coming together, okay, to create the vector equilibrium, right? So 8 of these coming together to create the vector equilibrium. And when I realized that, I saw that the star tetrahedron is 8 tetrahedron pointing out, and that the vector equilibrium is 8 pointing in. And now I had both sides of the event horizon, the radiative side and the contractive side, all in one mathematical metric that was producing both to generate the feedback of creation. I was really excited then. I mean, people would, anyway. my van was bumping around, you know, and it's not because I had a girlfriend. And so so I realized this, and it was like the 8 star tetrahedrons coming together to create the vector equilibrium in the middle. Just like this. And when the whole thing was put together, it would generate a vector equilibrium in the middle, right? The vector equilibrium in the middle. And then it would generate the next fractal vector equilibrium on the outside, right? And so it was a radial growth generating scale in the vacuum. So I was really excited. I thought I found something very significant. I was looking now to solve this and in terms of physics. How does it apply? How does it, you know, emerge in the physics? And as well, I was starting to think, well, this physics must have, you know, angular momentum, must have dynamics to it. This is not a static thing. This is a fluctuating thing. So how does that all compute? And, you know, I was doing research in advanced physics and all this. I came across a graphic on the internet of a phenomenon that's called crop circles. And that graphic was a perfect representation of the fractal structure of space I had just described and found in my van jumping around. Now I know that there is hoaxes out there and hoaxers out there, and I know they make crop circles at night with their gumboots and drinking moonshine and stuff. But there is as well a lot of genuine phenomenons that goes on with these crop circles, where it's not obvious to just write it off as people jumping around with gumboots. Or Doug and Dave out there, you know, having a good time. What got me really interested is that there was a bunch of croppies, people that photographed these things and measured them and all this, that had gone into, you know, they figured out if somebody is trying to talk to us, whoever that is, maybe we should just try to talk back. So they got some gumboots and they went in there and they stomped around in big letters in their field. What do we need to know? And the very next crop circle that came out was this. And that really, you know, struck a chord with me. And if you look carefully, you can see that the way the crops was laid, it made an effect of light and shadow in which you could see the vectors of the tetrahedron that would be creating this metric in three-dimensional space. Now that's not obvious to do in the middle of the night, in the middle of a field. All right? This is not a small thing. It's a large thing, and it's very, very accurate. And then a few weeks later, they seem to insist on the pattern. Another one, just like the first one. And this one with another set of information in the middle. In this case, there was another set of fractal division that was going on in the middle. And when I looked at it closely, I realized that that set of information was the exact same structure of division, those triangle divisions of space, or these tetrahedron division of space, but in this case, pointing in the opposite direction, going inwards towards infinitely small. Never mind the fact that if I overlaid the octahedron part of the 64 tetrahedron grid over top the crop circle, it was a perfect fit. This compelled me to continue to study these things And as I was studying advanced physics and continuing to advance my theories, and I realized that there was eventually crop circles that were perfect representations of the 64 tetrahedron grid that were emerging in the crops of England. And then vector equilibriums coming out of the crops of England with singularities at their center, including the information about the boundary generated by the tetrahedrons, so that if you knew that each tetrahedron generates its own boundary, then you would add them here and generate this other geometry which has been popularized as the seed of life, and then a crop circle to tell you you've decoded right. And so this was like a code that was being given. I was very excited about that. I continued to study it, and there was very much information that was coming out of the crop circles that had to do with fractals, the way those spheres, okay, each boundaries of the tetrahedrons divide. Here we can see it in another crop circle where the central part of the sphere divisions it has these crescent that seem to indicate rotation, angular momentum, which is what we're going to get into in a minute or after lunch. And then that division of space was fractalized over the field. And then eventually even structures like this that showed these spheres dividing in a rotational pattern. This one crop circle right across from a very well-traveled highway, which has Stonehenge on the other side. Okay, very large crop circle that appeared, and then even larger ones, like so, that showed that spiraling division of space, that dynamic. And now I was starting to really link into I believed I had found a fundamental structure of equilibrium for the vacuum state. Now I had to understand the dynamics that fundamental structure generated in the field equation, the dynamics of it, not the static view of it, but the dynamics of it, the angular momentum, the rotational part of it, the field equation that emerged from it. Because remember, the vacuum state geometry would be the structure that goes towards infinitely small, that collapses into singularity. There's the other side of the equation, the feedback, which is the radiative side, which has all these energy levels and all these dynamics in it, and that had to match to the geometry of space. From this seed, how would the field get generated? I had the static model of the structure of the vacuum, but that was only the vacuum state moving towards infinity. I didn't have the vacuum state generating the electromagnetic radiation from that division of the space. And so I started to, realize that they had to be angular momentum, they had to be spin involved in the space-time manifold to generate that boundary. In order for the vacuum to generate a boundary, it had to have some kind of shearing, and in technical terms this is called shearing modulus, that would divide the space, that would fracture the structure at very specific intervals. And I was thinking about it, and I was studying and studying, and then eventually it came to me, and I realized, and it came to me in different ways. I realized that they had to be gyroscopic reasons. They had to be gyroscopic dynamics of the angular momentum of the metric of space, and I start to study gyroscopic effect, angular momentum and Coriolis forces and all this, and I start to study deeper and deeper in physics and especially in Einstein field equation how we dealt with rotation and angular momentum, and I realized that in many cases we in general try to avoid spin and angular momentum. We try to make things freeze up so that they can get simpler and easier to map out. But when we do that, well, then we most likely lose a very important component. And then I realized that we had done that with something very, very fundamental. And I started to study how Einstein came to his equations and how his equations were solved. So Einstein did this. He basically, in general relativity, he extrapolated that gravity may not be an internal force of an object, but instead the force of that object applied to the structure of space-time itself. And the way you can describe it simply, imagine a surface of a trampoline. And that trampoline has a big ball, a heavy ball on it. Now the surface of the trampoline around the ball is going to curve like this, and that you could call space-time curvature. And if you took another ball and you put it in the trampoline, it would want to rotate or roll or have an orbit around that first ball because of the space-time curvature around it. This is the typical visualization that you get from space-time curvature. When Einstein wrote this idea of this metric, curving and creating this space-time curvature, he didn't solve it. He just threw out the idea, basically. And he published it, and he thought it's going to take a while before this is solved because it's really complex. But there was a German physicist on the Russian front that got a hold of his paper. His name was Carl Schwarzschild. And he thought, hey, let's try solving this. So while dodging bullets and being sick and everything, he solved Einstein field equations. And when he did so, he simplified the equations, he simplified the models so that it would be easier for him to do a first approximation. And the way he did that is that he assumed that the object had no angular momentum, no rotation. Okay? So he solved the equation for something that's not spinning, because it was the first approximation. He sent the result to Einstein, and Einstein was so impressed that it was already solved, that a solution had already been found. He right away sent it to the Prussian Academy and got it published. And so that was the first solution to Einstein field equation, and it's called the Schwarzschild solution or the Schwarzschild radius. The thing is that when the Schwarzschild radius was solved, when Einstein field equations were solved for the first time, the result of the solution was nothing else than a black hole. Okay? That is, when he tried to solve the solution to calculate how much gravity something produces, you had to have infinite potential in the middle to solve it, meaning it creates a nonlinear infinite potential at the center. His equation predicts black holes. And that's why right away there was talks about how this equation could predict something like a black hole. But, you know, at the time this was highly theoretical, and nobody had ever thought that they would like actually come across a black hole in the universe. So everybody basically ignored that part of the equation and said, well, we can use the weak curvature to predict, you know, the curvature of light around the sun, or how something would land on a, you know, how much planets or how much galaxies, you know, they rotate and how they're organized. Now, I was, you know, this was very interesting that the high curvature of the equation was never truly fully acknowledged, because when you approach the center of the equation with the curvature of space-time, the equation of Einstein goes towards infinity. So remember, I was telling you everything is a black hole because it's divisible to infinity. Well, here you have Einstein field equation telling you that it is so. That in fact you need that singularity in the middle in order to even calculate the weak curvature. And basically what we did is we used the weak part and we just let go of the other part unless it was called a black hole. What I'm saying here is that that first approximation had no rotation and predicted black holes. Okay? So eventually, with Elizabeth Rauscher, we wrote a paper. This is the title of the paper, The Origin of Spin, a consideration of torque and Coriolis forces in Einstein field equations and grand unification theory. This is a paper that's in peer review right now. It's a result of what I'm talking to you about. This is a new solution to Einstein field equations. Okay? There was a solution that was given to Einstein field equation after Karl Schwarzschild. It took a very long time. It wasn't given until 1965. In 1965, the Kerr and Newman solution was rendered, in which you had a black hole, or the object was allowed to spin and have charge. So it had spin, angular momentum, and charge. And it took all the way from Einstein writing these equations to 1965 before that was able to be figured out. So you can imagine the complexity, and this is basically the solution that's mostly used to interpret what we see around stars, black holes, galaxies, and all this. There's a problem though. When you take these solutions and you apply them, for instance, to a galaxy or to the universal size, the result of the equation does not match observation. Okay? The result of the equation only predicts 4% of what we see out there. All right? That is, in order for the universe to look the way it does, or for a galaxy to look the way it does, with the amount of mass that we are seeing in that galaxy or in the universe, and when we put it in the Einstein field equation, it doesn't match. What they have to do, and what they've done, which I believe is a complete cop-out, is that they've added the 98 or 96% of the mass that's missing and the energy that's missing. They called it dark matter and dark energy. It's very, very convenient. Instead of revising the equation, they assume that it's something out there that they cannot measure and that they cannot see. So that's very convenient, because who can tell them it's wrong? Right? They've been looking for dark matter and dark energy since then. I mean, it's been, you know, almost, I mean, at least 10 years of funding and detectors and all sorts of experiments to detect dark matter and dark energy. Now, I think they will detect something. However, I don't think it's going to be what they think it is. I think the error is in the equation. And the error in the equation is describing, if this error would be corrected, would describe something that's out there, but that's not dark matter or dark energy. It's only a force that allows these dynamics to happen. And that force, I realized, had been omitted. And I'm going to show you how I found that out. I studied the Kerr-Newman solution that had finally added rotation into the space-time so that if an object was rotating, they could calculate that as well. The thing is when they did so, they wanted to get rid of complexity as well. Because angular momentum and gyroscopic effects are so complex, they did something very strange. They decided to eliminate the gyroscopic effects of rotation, like eliminating Coriolis forces and torque and things like precession and all this. Well, how would you do that? Well, the way they did this is that they attached the frame of reference to the rotating metric so that there would be no force. Now, this is a little trick that's used in physics and that really tweaks the results. And because this is buried under enormous amount of complexity and very little people on this planet understand these complexities, it is not being noticed until now. Now, what they did is this. Imagine this. You've got a shaft that's turning, maybe on the lathe here, right? Or maybe there's a V8 motor spinning this shaft, right? And it's spinning at 5,000 RPM and you're in front of it. And in a moment of illumination or in a moment of extreme stupidity, you grab onto that shaft, all right, with all your might. Well, you're going to experience some effects, okay? Those effects have to do with shearing, like your skin flying off, heating, like smoke coming off your fingers, all sorts of effects like this that are certainly uncomfortable and that have to do with the force of torque applied now to your hands, right? That's forcing that shaft to spin. All the 300 horsepower of that V8 motor spinning that shaft. Well, if I grabbed you at the exact moment that you went to grab that shaft, if I grabbed you on your center of gravity and spinned you at the exact same rate, you would feel no force. You would feel no effects in your hand. It would be stationary relative to you. You see? However, I could still say that I'm accounting for angular momentum because I could count the turns that you're going around. So I would have a frequency rate of angular momentum. You see? And that's what they did. Why did they do this way? It actually goes all the way back to a fundamental assumption that was made, that things are spinning in a frictionless environment forever. That is, the assumption is, because if you ask a physicist, what is making the Earth spin? They'll tell you it's because it's in the solar system that's spinning. Then you say, well, what's making the solar system spin? They say, well, it's in the galaxy that's spinning. Well, what's making that spin? Well, that's in the supercluster. Well, what's making that spin? Well, that all started in the Big Bang. You see, son? If it had the Big Bang... Sorry, I'm being cheeky. There was the Big Bang, and then all the energy through everything spinning, and it's been spinning in a frictionless environment since then. So we don't have to account for spin because it's inherent to the Big Bang. First of all, that doesn't tell you where the energy came from to generate that moment of impulse, but certainly it's a very, very large generalization because when you look around, we just happen not to be in a frictionless environment. I mean, it's the same thing at the atomic level. They tell you that electrons spin perpetually because of being in a frictionless environment. They got spinning at the Big Bang, and they're still spinning now at 99.9 something the speed of light, right? Those electrons. Now that's a lot of spin for a long time. And when you look out there, it just happens that it would be true if there's only one atom in the universe. But as soon as you have two atoms, now you have interacting fields. You have friction, you have collision, you have all sorts of things happening. Gravitational fields acting on each other. Not only that, in order for that statement to be true, then all objects would have to be solid, true and true, homogeneous, which we know they're not. For instance, the layers of the sun rotate at different rates and have huge amount of frictions between them. Think of the inside of the Earth. Is the inside of the Earth spinning in a frictionless environment? I don't think so. It's spinning at a different rate as the surface, obviously because we're getting a magnetic field resulting from a dynamo effect. So what's making the inside dynamo spin against the mantle? You're talking molten lava, not frictionless. Not frictionless at all. Solar winds in our solar system, the gravitational pull of the Earth. You see, here I have two eggs, and don't worry, I'm not going to throw them at you guys. That would be a first, eh? The presenter throws eggs. Bad crowd. Here I have a hard-boiled egg. Fairly, constant density through and through. Okay? Here, an unboiled egg. High level of viscosity in the middle. Okay? I'm going to spin the hard-boiled egg on the floor. Now imagine this hard-boiled egg was in a frictionless environment, or a very low friction environment. It could spin, oops, let me try that again. It could spin constantly and homogeneously as it does here and slow down, but that's mostly because of friction on the floor, right? Now let's imagine that it was frictionless, but you could see how that could be possible. But now, let's try to spin an egg that has high viscosity at its core. It stops very quickly. Most of the angular momentum is absorbed by the viscosity of the central core of the egg. Galaxies are just like a non-boiled egg. It has all sorts of density, plasma density change, all sorts of friction, and all sorts of different levels of viscosity, and so is the center of the Earth. There is actually currently no appropriate geological description on how the moment of inertia of our inner core of the Earth occur. How do we get a magnetic field, and what's spinning that dynamo in the center of the Earth? Did you guys have bicycles when you were kids that had those little dynamo on the wheel that created enough current to put up a light in front so you could see at night? Well, in order to spin the dynamo, you still have to pedal. So there's got to be somebody pedaling. There's got to be something forcing things to spin. The new solution that we wrote detached the frame of reference from the rotating metric so that we have an appropriate description of the physics at hand. And the result is that you have torque and Coriolis forces applied to the system directly from the space-time manifold. So let's go back to the analogy of Einstein's field equation of the trampoline curving to generate gravity. So basically Einstein said gravity is the result of space-time curving like the surface of a trampoline. And basically what we say in this paper is that yes, and when space-time curve, it doesn't just curve, but it curls, just like water going down the drain, and that generates spin, angular momentum. And that's the source of the spin of all things. And that is an appropriate way to actually describe physics of angular momentum in the universe. So when we add torque to space-time, the solution gives us a very different picture than a perfect sphere. It generates a torus structure, okay, which is a sphere with two holes in the middle at the north and south pole. And because it has Coriolis forces are the forces that makes water rotate in one direction in the north hemisphere and in the other in the south hemisphere, that makes hurricanes rotate in the opposite direction, that makes plasma dynamics on the sun rotate in the opposite direction. Because Coriolis forces were added to the equation, so what we did is we added a term for torque and the Coriolis forces as a secondary rank tensor on the space-time manifold. The result is a double torus structure, a double torus manifold that has this dynamic, which is viewed here from above as a rotating yin-yang sign, if you'd like. Right. And so that's quite a different picture. And it's quite a different view of the universe, because now space-time is the source for spin, for Coriolis forces, for the magnetic fields, and now we can start to drive the whole equations of creation based on this space-time torque, generating even gravity and electromagnetic radiation. Because you see, now we have a direct balance equation. This is the next paper we're writing right now, is the balance equation that shows that there's a balance between how much space-time torque, how much force is applied on the system, and how much shearing that generates, and how much radiation the system outputs. So now you have a feedback between the gravitational field and the space-time torque. And that was the dynamics that I was looking for. If we look at the torus, from above, what's in the middle? Space, vacuum. The middle of the donut has a hole. This is where singularity would be in the center of a black hole. So at the center of the space-time manifold, where we would expect the Planck's distance at singularity, we find the vacuum state polarization. This is why the vacuum has polarity and structure, because space-time has angular momentum, is rotating, which generates acts of rotation that generates structure in the space-time manifold. And so we approach the center of the torus, we approach that point towards the Planck's distance, and we used group theoretical models to look into there, and solve that point for subatomic particle. And when we were able to solve all the subatomic particles, okay, for that point, all the particles we observed, subatomic particles for that point, which were now linked in our mathematics to the space-time manifold for Einstein field equation for large objects, when we went to that point, the solution gave us a vector equilibrium. Okay? This is a solution given out of a set of mathematics that had nothing to do with my instinctive and logical thoughts that have brought me to believe that this had to be the geometry of the vacuum, the geometry of singularity. Yet the mathematics totally confirmed it. This all came together in a beautiful way that generates a full unified field theory in which the dynamics of space-time is that feedback loop between the gravitational field going in and the electromagnetic field going out, and the center vacuum structure, the singularity, which is the fractal space-time grid that defines that field equation. All put together, you get all the particles of subatomic particles and all the mathematics you need to solve gravitational fields, the electromagnetic field, the strong and weak force. Thank you. So there's still a lot of complexity built in. I think that complexity is going to really reduce when this is fully understood, because I believe we can make way with the strong and weak force. I think those are inventions of humans. They have nothing to do with reality. They have nothing to do with the atom. You see, what happened is they discovered nuclei of the atom, and they found that there was protons in it. Those are highly charged, positively charged particles. If you take two positive magnets and you try to push them together, you're going to get a repelling effect, right? Now, when they calculated how much force you would need to push these particles into a nuclei of an atom, those protons all squashed together, that close together, they calculated the force you need to do that had to be extraordinary. And so they said, that can't be gravity, so we'll just invent a new force. We'll call it the strong force. It's strong. And what are we going to do? We're going to make it be mediated by gluons, because it's gluing everything together. Well, okay, that's one approach to physics, and then you can say, well, you know, it's there because we calculated it, but you didn't really ever experience it. You never even measured it. You just think it's there because you can't imagine how those protons could be together without it. Then they found the quarks, and they said the quarks are inside. You see, inside the protons, so they are squashed even smaller. So then they had to have an even stronger force. But they didn't want to add another force. I mean, that would look goofy, right? So they just said, well, that's the color force, and actually the strong force is just a residual force of the color force that's really strong in the middle. Well, if you make calculations for a black hole atom, and you calculate how much gravity there is at the nuclei level of a black hole that size, you have exactly the force you need to keep the atom together, to keep the nuclei together. You don't need the strong force. You're dealing with gravity in the vicinity of a singularity. You understand? And so now you can make away with that force. And so that starts to change your picture of the weak interaction and all this as well.
I would like to interrupt this presentation to give a little more details for the more technical audience. Here I'm describing the atom as a mini black hole. Many would say the atom doesn't have the mass necessary to be described as a mini black hole. However, In this presentation and in my research, I have come to conclude that the atom is interacting with a very highly structured dynamic vacuum, feeding it its energy potential and its density. And as we've seen in the presentation, the density of that vacuum is extremely large. I believe the vacuum is a highly structured, coherent energy that is feeding the atom and that is producing the dynamics that we see as particles and electron dynamics. In this view, then, the strong force becomes the gravitational force in the vicinity of a mini black hole produced by the vacuum structure. The electron is spinning at near the speed of light as a result of it being in the vicinity of the event horizon of that mini black hole. All this gives us a brand new picture of the physics of creation. Let's continue with our presentation.
What I'm bringing in is that, wait a minute, by modifying Einstein field equation, we might be able to solve for all this and not need so much quantum theory, which is quite a change in the optics. This is one of the things that Einstein believed all of his life. That's why he was never keen on quantum theory. That's why people say that he dropped out after he wrote his field equation. He didn't really want to participate anymore. He believed that with his equation, he should be able to solve all the way down to the subatomic particle, and he actually got really close, I believe, at one time, because a French mathematician contacted him was giving him solutions to his own equation that incorporated torsion. Torsion is the distortion of an object. If you apply torque to an object, imagine you have a 2x4, and you hold the bottom and you twist the top, you're going to get a distortion of the object. Okay, that's called torsion. And so this is Élie Cartan, thought that, you know, maybe we could solve Einstein field equation just by describing the torsion or the distortion of space-time around a gravitational field. And he solved it. The thing is he solved it, and it gives the exact same answer as Einstein field equation. So everybody said, well, it doesn't teach us anything more, and it's more complex, so they dropped it. The only thing is that in order for something to distort, you have to have torque in the first place. And that they never went to. They never added the torque to the space-time manifold. If you are missing 98% the mass of the universe, okay, you most likely missed the source of force that is creating what you are observing. And I believe that source to be space-time torque. Okay, the force that spins a galaxy. Imagine if you had to build a motor, how many horsepower you would need to spin one galaxy with 300 billion stars in it. A lot of force. Imagine how much force you would be missing if you didn't account for that engine. Right? That would be like analyzing the wheels of your car, okay, and all its dynamics, its mass, its angular momentum, and everything, but omitting to add to your analysis the V8 engine that's spinning it. Now, when you look in nature, you can see these dynamics. Look at this. This is a galaxy, okay? And galaxies have galactic halos. Can everybody see this? It's like a very fade, big sphere around the galaxy. And when, when we look at galaxy, typically we only think of the galactic disk, right? And that's because in the galactic disk, there's the most amount of density because the sphere around a galaxy has a huge surface, so things spread apart, so it's not as easy to see. but there's actually more stars in the galactic halo around galaxies than in the galactic disks. And then here you can definitely see a huge vortex going into the black hole at the center of the galaxy. We can't see the one below it because, you know, these are very far away and we don't have that great of optics and so on. But we know that in general, there is always, or typically, two huge vortices going into center of black holes. In the case of our galaxy, that vortex is, I believe, 3 on the north pole of our galaxy, if you're looking from our perspective, is 3,000 light years long. 3,000 light years long. This is, at the speed of light, it would take still 3,000 years to get to the end of the vortex. And it's filled with gases and high velocity dynamics and high energy dynamics, enough that it's actually visible thousands and thousands of light years away from it. Imagine how much torque you need to produce that. Isn't that an obvious example of water going down the drain? Okay, now you'd say, well, wait a minute, when we see these vortices and we follow the particles, they're spitting out. Okay? Well, okay, if water is going down your drain, air has to move out of the drain for water to come down. That's the exchange. We only see the outside of the event horizon. We only see the radiating part of the event horizon. We don't see the space-time torque going into it to force the system to have angular momentum. And so the result is that we live inside a black hole. That's why it's black out there at night, okay? And what we see inside that black hole are smaller black holes, smaller scale black holes, that we're on the outside of. So what do they look like? Radiating stars, radiating objects. Because we're on the outside, we're seeing the plasma Coriolis forces dynamics on the outside of the thing. We see the radiative side, we don't know about the contractive side, and that's why most of our physics is based on the radiation. But there's an exchange between the two, and this is the exchange I'm showing here, and that we calculated. These are very large objects, blazars, quasars. They're all being photographed to have these huge vortices. They're enormous. We see them at all scales. This is a quasar. So here you can see 10 to the 6 light years long is this vortex. That is 1,000,000 light years long. Okay? 1,000,000 light years long vortex. At the speed of light, 1,000,000 years to get to the end of it. And these things are spinning at near the speed of light when they arrive at the event horizon of the black hole. So very, very high torque. Big engines out there that are not being calculated. Now this is the different scale. Those are called microquasars. We find those even inside our own galaxy. And in this case, the vortex is only 3 light years long. So now you're starting to see the scalar dynamics, the scale change, the fractal nature of the division of space. From quasars to microquasars to cloud stars or supernovae, we see the same dynamics, the same vortex. Look at this vortex dynamic on this pulsar, which is the result of a supernova explosion. Have you ever seen articles in a layman physics magazine where it says the death of a star explode into a supernova? Okay. We haven't ever experienced the death of anything. We haven't observed that. We really haven't. All we've observed is things changing state. Okay? For instance, I'm not talking esoterically here. For instance, people have all sorts of debate about if life continues after death or eternal or whatever. You don't need to be esoteric. Just take, what you got and extrapolate from it. You have a few billion atoms. There's a lot of cells. There's 100 trillion cells in a human body. And they're all organized in an organized matter. And then all of a sudden, they disorganize. Okay? However, all these atoms are still spinning. You haven't lost one. Okay? They're still out there. They're still spinning. In fact, you might be made out of the atoms of your neighbor. And your neighbor might be made out of your atoms. And so there's no evidence that things actually stop. Because if there is space-time torque going to singularity in each point, then there is angular momentum at all levels and things continue spinning no matter what. What I'm saying is that the friction that's out there is overcome by the space-time torque. So, and that makes it appear as a frictionless environment. So we don't see death. We just see things changing levels of organization, changing scales. And when we see a star exploding, right, they call it the death of a star. But when they focus on that same area afterwards, what do they see? They see a pulsar. Oh, that's nice. They just changed the name from star to pulsar, so the star is dead and the pulsar is born. Let me give you an example. If you were a camera inside a woman's womb, and this woman was pregnant, you would see life developing in that womb. And after 9 months, you would have probably a pretty good relationship with this life inside the woman's womb. All of a sudden, there's a big earthquake in your world, and waters disappear, and there's an opening that opens in the little black hole at the end of this hip joint, and this being that you had a relationship with disappears through that hole. You would experience death. You would think this being is dead. The person on the other side experienced life crossing the event horizon. Right? So what I'm saying is that our mathematics and our views have now shown us that actually pulsars and supernovae explosions are the result of stars. When space-time is torqued into a certain radius, and it generates material inside, so that the Big Bang is only one of those events that generated the atoms of our universe, that atoms are actually being manufactured at the singularity of black holes. And that's the exchange of those atoms coming out, those vortices, as the space-time torque influence those black holes. And when those particles get out of there, they are stuck in the gravitational field of that black hole and accrete on the surface of the event horizon, as well as other atoms that are created by that black hole as it travels through space. And when it accretes too much material, it becomes unbalanced. There's too much radiation for the contractive torque force at the center of the system. The system slows down too much, and the instability generates an explosion. It blows up. What it does, it releases a layer of material so it can regain stability. And so that's what we see. and then it regains stability, and when it does, guess what? The radius is much shorter, the ballerina has brought her arm in, so the thing spins way fast, like a pulsar. Okay? And then if it's fast enough, then we call it a black hole, and we say, look, the star made a black hole. And what I'm saying is, no, the black hole was always there. What we observe now is the dynamics of that black hole much closer to the event horizon, so we see the X-ray emission and all this stuff that we wouldn't observe before. By the way, all these things are X-ray emitters, from atoms all the way down to up to galaxies and so on. So do you see how the picture is a little different? Now we start to see the universe as cycles in space, okay, instead of start, stop, start, stop. And you start to see that maybe, just maybe, that's how our universe was created. An enormous black hole that became unstable and blew out a certain amount of its orgosphere, a certain amount of its plasma, which generated all the rest of the stuff we see today. And that those cycles most likely go on and go on and go on forever. Even the dynamics of the Earth plasma, like the dynamics of the Earth stratosphere and the way hurricanes and weather systems move around the Earth, obeys those conditions. That is, the weather systems go from the North Pole down to the equator and then back up. And from the South Pole up to the equator and then back down. They don't cross over. And so on. So there is those dynamics, those plasma dynamics are seen at all levels. In the sun dynamics, we see the exact same pattern, that double torus pattern, in the dynamics of the plasma around the sun. So, and what we see in these dynamics, we see Coriolis force, and in the center of these vortices, what do we see? We see a black spot. We call it a sunspot. And typically we've been told that sunspots are surface events, and I debated this for 15 years, and finally they're finding out that they're not. They're vortices going towards the middle of the sun. Because what you're seeing in a sunspot is a vortex, Coriolis forces going towards singularity, and that's why they're most commonly matched by another one on the exact opposite side, right, that meets at the center. So those dynamics between the sphere dynamics and the geometry of space that we saw earlier, between the field dynamics, which would be the sphere around each tetrahedron, and the structure of the vacuum that generates it, that maintains it, we can see that these dynamics are actually present at all levels, even at the biological level, as I was saying earlier, and even you got here by going through these vectorial array dynamics in the womb of your mothers. I point that out all the time. It's like, you want a proof of the fractal nature of space? Well, have you not noticed? People take that for granted. People come out of other people. It's an amazing thing. They do. I mean, I have pictures of my mom with her grandmother, with her grandmother, and like the cousins and everything, and you can see the fractal link of all the mothers, you know, through space-time. I mean, it's freaky. People coming out of other people. I mean, it's pretty obvious it's a fractal structure. And so when you look at the way it happens, even the woman's womb, well, the first cell divides into two, and then the two into four. And when they do four, they arrange into a tetrahedral array. And then these four divides into four again, into two each, making 8. and those 8 arranged in a star tetrahedron array. In all of this, you're starting to see, in any case, that this very fundamental geometry is actually how you emerged into this world. You went through that structure in order to get here, and you went through it through the molecular interactions of water. And if we look at what really generates this placements of molecules or cells, well, there's a strand of code inside the nucleus of cell that we call the DNA code. And this DNA code is really, you know, an interesting thing, because if we look at the dynamics of that code, it has that spiral kind of torque field look to it. And assuming that these energy levels for cells are correct, and that we can actually describe the cells as like mini black holes interacting things, we would see that at the nuclei, we would see that at the center of the cell, we would see these spiral-like structures. But, and you know, there is a lot of code in your body for you to be here. The complexity is outrageous. I mean, seriously outrageous. If you take the DNA that's in your body, in each cell, there's approximately 6 feet of DNA. And if you put all these strands of DNA end to end, you could wrap it around the world 5 million times around the world, 4 to 5 million times around the world. 4 to 5 million times around the world. That is inside your body right now for you to be able to function, so that all the cells know what everybody else is doing, and everybody is organized, and all the information is moving through, and all this is happening because there's a fundamental codonic interaction of the proteins that permits it. And guess what that code is based on? Well, the codon structure of DNA are based on a 4 to the third, you know, relationship, which is 64 codon possibilities of combination. I find it interesting that this, you know, 64 possibility codes that generates the amino acids of DNA and so on matches what we call the affine connection metrical space that Einstein used to produce his field equation, the space-time manifold. It's called the affine connection, and it has a 64 element metric that generates a component for the space-time manifold structures. So then we have a direct link here between the space-time information, the space-time torque, and the way DNA is. Like DNA is like the transducer from space-time information moving through into the world and gathering information. You're like a probe for space-time looking back at itself from the outside and gathering information about its existence. Now, please don't go to your shrink and say, I think I'm a space-time probe, because you might get in trouble. But this is a very exciting kind of view that, like, we're starting to see the relationship between the space-time structure and the biology, and how biology moves through things.
Thank you for joining us today in Crossing the Event Horizon. Nassim Haramein's research is supported by the generosity of the public. To directly participate in this most crucial work, see our website for more information on how you can stay involved. by visiting www.theresonanceproject.org. Thank you for continuing to spread the word about this exciting work and recommending this DVD to your friends and family. Be sure to watch the special features portion of this DVD.